Kia ora koutou, everyone. Welcome to the OERC seminar series. So today we have a speaker, Melissa Kozul, speaking today. She's a lecturer in power generation propulsion at the University of Melbourne. And she does research on numerical simulation of turbulent flows critical to the performance and stability of key energy and transport technologies. And today, Melissa is going to talk to us about improving the performance of gas turbines by applying micro-riblet surface textures to high-pressure compressor blades. So a bit of a mouthful of a title there, Melissa. So over to you. Thanks a lot.
Thank you for the introduction. So I think I have a few things to explain here. Hopefully I'm able to do that. Thank you everybody for joining. And yes, today I will talk about, first I will introduce gas turbines a bit more. Maybe most people don't think about them as much as I do, and why they're important both for New Zealand and for Australia. And what we can do to keep supporting their development and their increases in efficiency that we've seen over the last few decades. Okay, so what have I done? Okay, so I want to talk about the reason why I got into engineering in the first place is to look at the energy transition, to work in the energy transition, and I want to talk now about the important role of the gas turbine in this energy transition. Some people think this is an old technology that needs to, I guess, disappear, or that it's dirty, but I want to argue for another view of how the gas turbine is supporting the energy transition. And so we see them in two main places. So on the left here for grid scale energy production. So this is a 15-meter long turbine that we can see. We can see a man in the back in blue. This is around 300 to 450 megawatts. And I want to point out the incredible energy density that these gas turbines represent. So this one 15-meter long turbine is about 100 to 150 wind turbines with rotor diameters of 120 meters each. So it's that is one of the big pluses of the gas turbine in the grid. And here it's spinning a generator, but the other main application of them is, of course, in aviation. And here we have two gas turbines on each wing on this plane. But here the gas turbine is spinning a fan, which is generating thrust for the airplane. And so these are the two main places where we see them and where I hope to argue that they're really indispensable. So firstly, if we look at, on the topic of the energy transition, the emissions by sector in New Zealand and what's happening. So this was very interesting to me because the picture is very different compared to Australia. So in New Zealand, you have a lot of methane emissions from livestock. And actually emissions from electricity generation is quite small. It's only about 3.5%, and this is because you have a lot of hydropower. However, you can see that the transport emissions are quite high, and some of this is, well, a lot of it is actually related to aviation because of New Zealand's position in the world, and also a high proportion of people having origins from other countries. So there's a lot of travel back and forth to New Zealand. And obviously, you can't take the train overseas, so you need to get on a plane. And so what we've seen in the last few decades in New Zealand is a large increase in especially international aviation, emissions from aviation. There was a sharp drop because of COVID, but from a more recent report, we've seen that domestic travel has returned to pre-COVID levels in more recent times. And so this is a big source of emissions in New Zealand. So these from the gas turbine. Now there's lots of hype around electric or hybrid airplanes. Here we have one model being developed by Airbus. There are more radical airplane designs being designed like this, being thought up like this blended wing body designs that are further along than I actually thought. But this is quite a radical design. It's going to take a long time for this to be used commercially, especially. And the electric aircraft are only really useful because of the weight of the batteries, are only going to be useful for short trips and low numbers of passengers, so just a few passengers. For the long range, large aircraft that New Zealand is reliant on, this aircraft, this sort of tube in the sky powered by gas turbines is for the foreseeable future what is going to be used. And so this talk and my work here is about continuing to improve on the energy efficiency of these turbines. And so, as I've just mentioned, efficiency is a big point here. The other big issue around emissions in aviation is using alternative fuels. So if anyone's heard of sustainable aviation fuels, there are big problems around producing enough of this, however, and so that's an ongoing issue, and they're going to be more expensive. So this ties back into the efficiency issue. So if our engine is using less fuel to begin with, then it will promote the uptake of those sustainable aviation fuels, which are going to be more expensive, at least in the beginning. And of course, there's the moral question of travel, whether we should be taking the plane or not. But I would argue for the connectivity offered by aviation is something worth fighting for. Okay, now if we look at Australia, and it's a very different picture, and actually we have the largest piece of the pie of our emissions is from electricity. And this is because of our historic and ongoing use of coal, especially in my state of Victoria. I think still 70% of our electricity comes from coal. And so the gas turbine has been used in Australia as a sort of, as the coal-fired plants come offline. There have been more use of gas turbines in the grid, basically to balance the grid with renewables. So when there's no sun shining or no wind, not enough wind power, the gas turbine comes on in about 30 minutes to balance the grid. Especially in Victoria, we have these peaking plants. And so what you see over time, this is for the whole of Australia, in time we have if we look at the coal curve, which is in green up here, coal use peaked in Australia some time ago and has been on the decline as those old coal-fired stations come offline. But the use of gas in Australia has been increasing. So this is natural gas. And a lot of that has been in these gas turbines in Victoria, especially as peaking plants, as I said, helping to support the uptake of renewables by supplying power when it's needed on demand. Okay, and the other big use of turbines in the energy transition is for storage. So a big problem, I won't talk about it too much here more, but I wanted to state that one of the big issues in the energy transition is storage. And again, we don't have, in New Zealand, you have hydropower. That's the traditional method of storing energy. We don't, in Australia being much flatter and drier, this is not really an option. And so we are exploring other options for increasing storage aside from the limited hydro projects that can be, that are possible in Australia. And so if we look at the main types of storage that was proposed by this CSIRO energy storage roadmap recently, aside from the electric storage, so that would be in a battery, which is already commercial technology, these other types of storage, so mechanical storage, including things like compressed air storage, thermal, so creating heat that you can then use for a turbine, or chemical, creating fuels that you can store and then use on demand, that all of these technologies rely on a gas turbine eventually, or parts of the turbine. And so I want to argue again that we need to keep developing this technology to be more efficient and more reliable as we move through the energy transition. Okay, so I've talked about these two uses, main two uses of the gas turbine, but what actually drives their efficiency more broadly? And so if we look at the very basic, looking for opportunities to improve this efficiency, So if we look at the basic sort of thermodynamic, how we're looking at this thermodynamics schematic of the gas turbine, and we can do basic thermodynamic analysis of this, we find that so these are different curves. This is vertical axis is the cycle efficiency. And here we have on the horizontal axis the pressure ratio. And each of these curves is for higher and higher temperatures. The firing temperature, so the hottest temperature in the cycle, which is in the combustor and facing that high pressure turbine. So we see that generally speaking, for higher temperatures, higher firing temperatures and higher pressure ratios, we have an increased cycle efficiency in the gas turbine. And in fact, this is exactly what we've seen over the last decades in gas turbine development. So we see that from the 70s, we've gone from about a 30% cycle efficiency up to best in class is around 42% now, thermal efficiency. And this has been, and we can see on this table at the left, is moving down in time. And we see the most recent turbines here on the right on this plot are these H-class, J-class turbines. These have the highest efficiencies now, much more complex machines. And what we've seen in time, if we go down this table, this is sort of going forward in time, increasing turbine inlet temperatures and increasing cycle pressure ratios, just as we saw from the basic thermodynamic analysis. Of course, people have always known this, but a lot of this challenges around achieving such high pressure ratios and turbine inlet temperatures were materials problems and different technologies, especially with fluid mechanics as well, coming into it. So this has been enabled, I should say, by the development of new materials that can handle new alloys that can handle higher temperatures, coatings. More recently in gas turbines, we have now ceramic coatings. And I want to point out these firing temperatures now are actually hundreds of degrees above the melting temperature of the blades themselves. So it's pretty incredible. Modern gas turbines, it's like you're putting an ice block in an oven and it never melts. So this has been achieved with these ceramic coatings over the metal surface and also very sophisticated cooling schemes. So this is some current work being undertaken in our group here in Melbourne. One of the principal cooling schemes is this film cooling. So basically you draw cold air from upstream and you pump it through the middle of the blade and it comes out all these little holes on the surface of the turbine blade like a shower head and forms a cool film protecting the turbine from the very high firing temperatures in the combustor that we need for cycle efficiency. And so we want to study this more directly, the heat transfer, so the highest temperatures that you get over the blade, because this is risky for blade survivability. And so these are some of my colleagues that have done specifically work looking at the turbine. On the pressure ratio, this is our compressor. So if you remember that image that I showed before, over each stage of compression, we can only get about a pressure rise of 1 to 3. So increasing the pressure by a factor of 3. And so what you need now to get those really high pressure ratios is many rows of those compressors. You also want it to be more efficient so that you're getting the full expected pressure rise over that stage, over each annulus. And not losing energy on other types of inefficiencies. And so this is where my work now comes in and what I'll talk about today and why we wanted to put those micro-riblets, which I'll explain what they are later, onto the blade, because we want to increase the efficiency of each stage of compression to achieve these high cycle pressure ratios, which then mean our whole engine is more efficient and we use less fuel, or we can go further on our jet engine, on our plane for the same amount of fuel. So how do we study these blades in the gas turbine? Each of those, we saw those many rows, like rows of pinwheels in the gas turbine, all rotating around the central shaft. What's been taken traditionally, so if you want to measure what's going on inside this engine, is very difficult. And so this is obviously done for compliance and for final testing, but it becomes a black box. So basically the engine manufacturers put fuel in, ramp up the engine and see what is produced. See how much thrust or power is produced from this engine. But measuring inside, this thing is spinning, if it's an aero engine, it's spinning at tens of thousands of RPM. So it's impossible to measure inside. And it's also, as I was mentioning, those extremely high temperatures is very difficult to measure anything at those extreme speeds and temperatures. And so what people have done over the last decades is to study the blades. Each blade of in the gas turbine annulus is like a little wing. And so taking this annulus, unwrapping it into something called the linear cascade, and that this is an approximation for that annulus, and then placing this linear cascade, so these blades are now upside down, in a wind tunnel. Where we can do measurements upstream and downstream, usually of the pressure with pressure probes, and then to understand if I change the shape, if I optimize the shape of these blades, how I can improve the efficiency of my gas turbine. And gas turbine efficiencies really didn't start becoming competitive or improving until these sorts of studies really to work on the shape of the blades, to optimize the shape of the blades, came to pass. And the first linear cascade, so this is a picture from Germany, where there are many of these experimental facilities. We don't have any in Australia, so we work with these teams in order to get validation data for our numerical studies. But the first cascades like this, I was looking in the literature, is about 1942 in the US. So it was definitely a wartime activity into improving jet engine efficiency. Okay, so what does the flow around here? Now we get into the fluid mechanics. What does the flow look like around here? This is now setting. We care about these flows because it is dictating the efficiency of the whole engine. So we need to take a closer look at this engine. So in the gas turbine, we have alternating rows of stators and rotors. So only half of our gas turbine is actually spinning at any one time. And on the left, we have the stator, so that's stationary, and the rotor is moving upwards in this frame of reference that we have. And here we have the sort of pictures of some schematic of what the airflow is doing through the gas turbine. And we see that coming off this blade, we have a wake or something like a negative jet that's then ingested by the next row, and we get all these complex fluid flow interactions. And so plus on top of this is just a geometry picture of the main features. On top of this flow is turbulent because it's moving at high speeds. And so if we do a high fidelity numerical simulation of this, it looks more like this. So we can see a very complicated fluid flow. These are contours of turbulent structures inside. And so we can use computational fluid dynamics or CFD to use as used in design iterations to predict these. Mainly I'm interested in aerodynamic loads, but also you can use it for mechanical and thermal loads. And this is often then validated against that limited experimental data, even in the cascade configuration where they're mainly just measuring the pressure up and downstream. We can get a much fuller picture of what the flow is doing, and so look at optimized designs. What we're solving here in this picture is the fundamental equations for fluid flow. So this is basically Newton's second law rewritten for a fluid, the Navier-Stokes equations. And so this is a high fidelity, this is a very fine numerical grid. I'll show you a bit more of that later, sitting behind this picture and solving, giving a very high resolution photograph of the flow inside the gas turbine. But what happens, the picture that I just showed you just before lies on a spectrum of numerical approaches for solving fluid flows. So we were on this, what's called the direct numerical simulation side, and this is what I do. This is solving the equations directly with no modeling involved. But there's a whole spectrum. This is very expensive. I'm going to show you how expensive it is in a moment. we have a whole spectrum of numerical approaches where more and more of the turbulence is actually modeled and not solved directly, and where the grids are not as fine. And so on the left-hand side, we have what's called the Reynolds average Navier-Stokes equations. And this is actually what's used in industry, because these sorts of numerical approaches can be used on a laptop, essentially. And so if you need to test hundreds of designs, you're going to use a cheaper approach like this. But there's something nothing's free, okay? And there are issues with that approach. If we look at, this is simply the measure of pressure around a single blade. So imagine we have that blade that I was showing before, sort of that banana shape, and I put pressure tappings all around the blade. And this is what we're looking at. The dots here are experimental measurements, and the curves are from numerical approaches. And what we see with the green curve, which is one of these modeling approaches, is that it's mismatching just the pressure data from the experiment. And this actually is the top side of the blade, on this bottom side. And where it's mismatching, the flow is actually separating from the blade. It's mispredicting the separation of that flow from the blade, which is very bad. And this is an issue. We need to know this very precisely for our both to predict the efficiency, but even more practically from the engine operator point of view, the actual reliability of this machine. And so this is quite a big error for this case. Whereas this is a high fidelity method. HIPSTAR is our in-house code, whose development has been led by Professor Richard Sandberg at the University of Melbourne, and it really hits the experimental data very well. So we can predict these complex fluid flows that we saw on the previous slide very well with very good matching with experimental data. And then, of course, once we have this numerical test bed, we can then go on to do other things like, for example, put those riblets on, which I'll talk about shortly. The other problem with those models, they are obviously used by industry, so they are useful. What happens is that practically the companies developing this technology will tune those models to predict the flow correctly for their class of blade. But the problem is if we want to move out of that design space, then the models will fail. So they are not going to be a priori matching or giving anything real, if you like. So this is the problem. And this is why we then turn to direct numerical simulation, so high fidelity numerical methods, solving those equations of fluid flow directly in order to do something new, something more radical, to try to continue to support the increase in efficiency of the gas turbine, or of tomorrow's turbines, like to say. So this work, which I've published over the last couple of years, is in collaboration with GE Aerospace in Cincinnati, because we don't have turbine manufacturers in Australia. We definitely need to work with the companies overseas, and acknowledging my colleagues here from the University of Melbourne. So let's take another look at that cross-section of the gas turbine. We saw a picture over the top of it before, but if this is a cross-section of the turbine sitting under a wing of an airplane, usually we only see the front of it. So we just see the fan. But if you could cut through the engine, so cutting through, this is the nacelle here, so the cover over the turbine, you would see all of this amazing machinery inside. Now, as I said, to get those high compression ratios that that yields the high cycle efficiencies that we see in best-in-class turbines now, we need many, many stages of compression. So we have the low pressure compressor, and specifically I'm going to be talking about potential efficiency gains of the high pressure compressor today. Here we have the combustion chamber, and here are those really very high temperatures, 1600, 1700 degrees temperatures that come out and that hit the high pressure turbine, which is the subject of my colleagues' work, and is the other way that the efficiency has really been increased over the last few decades. So if we look at this high pressure compressor, We have from the literature that if the turbine stays the same, a 1% increase in the compressor efficiency results in an increase in the cycle thermal efficiency of about 0.5%. So this is a good target. Now, 0.5% doesn't sound like a lot, but given the many billions of dollars of fuel that is used and the many, the quantity of emissions that we're talking about in aviation, this is definitely the scale of things that engine manufacturers chase. Okay, so what are riblets and why are we putting them on this compressor blade? So they are well known from more fundamental fluid mechanics research. They're longitudinal ridges or ribs, longitudinal with the flow. So the flow is coming over the top of them in the same direction. And there's still some debate in the fluid mechanics community as to how exactly they work, but the main theory is that they are stopping the fluctuation of the flow in the transverse direction and therefore helping to reduce drag. Some people take inspiration or link this to shark skin. So if you look at shark skin under a microscope, it also has it has many other features, but it does have a dominance in line with the way the shark is swimming, these kind of ridges on it that are microscopic in scale. Now, riblets only work in turbulent flows. So that's when they reduce the drag. So because we have to have this fluctuating component, if it's a steady flow, they're not going to reduce drag. In fact, they will cause turbulence. Again, from these fundamental studies, we have S plus here is a viscous scale. So on the small scales of the flow, it's a type of spacing in the span. So now we're looking into the page at the shape of the riblet. Now, this is a measure of the decrease in drag over the surface. And so from these fundamental fluid mechanics studies where they swept through many different riblet geometries, many different riblet spacings, we know that if the riblets are spaced too far apart, they become like an obstacle, they become too large and they're an obstacle to the flow. So they will tend to increase the drag. That's not what we want. If the riblets are too small, too finely spaced, the flow perceives that surface as being hydrodynamically smooth. And so it doesn't do anything either, okay? But in the middle, there's a sweet spot where the riblets are actually reducing the drag. And again, these fundamental studies show maybe 5% reduced drag, up to 7% depending on the riblet geometry. So this is a passive surface treatment to try to reduce drag. And now there are all sorts of people putting riblets on all sorts of surfaces, including on the outside of the fuselage of a plane. But we're going to look at putting them on the inside of the jet engine to improve the compressor efficiency. Okay, so we're going to use this sweet spot found from the fluid mechanics literature and space these riblets in 17 plus units. Now this plus unit derives from a viscous unit very close to the wall, because those are the scales that we're interested in this sense. Okay, so this is what the simulation looks like. This is engine relevant conditions. So it's a geometry from the literature, because even though we work with GE Aerospace, they won't share their geometries with us. We use open geometries. That's also good for us because we can publish then the work. But the learnings are understood to be, this is a typical compressor geometry, and the learnings are considered to be translational. Okay, so we have a Mach number of 0.5 coming in, so we're at half the speed of sound coming into the engine. The Reynolds number, so this is to do with the speed of the flow, or the extent to which we have the Reynolds number in fluid mechanics is the separation of scales. So basically the ratio of the larger scales we have in the flow to the smaller scales in the flow. And this increases with fluid velocity. It also increases with scale. So you have very large, you have much larger Reynolds numbers, for example, on the outside of a plane fuselage than you do inside the engine. But this is an important thing that actually tends to increase the cost of our numerical simulations. So that's why we cite it. But it's important to match this to have the same fluid flow behavior as the engine. So these are real engine conditions. We have incoming turbulence. We're here modeling the turbulence that we would see from upstream. So it's definitely not a smooth flow coming in. It's been roughened up by the blades upstream. And this is a contours of the vorticity coming out of the page. So we see lots of different flow features. We see closer to the blade is much more intensely turbulent. And this area is called the boundary layer and is very important to understand, to control if we want to understand the drag. This is where all the drag lives over the surface of the blade. These simulations was completed on the then world's largest computer for open scientific research summit in the US. This is at the Oak Ridge Leadership Computing Facility. And we had an insight, what's called whoops, I don't have that here, an insight grant to be able to use these facilities because these simulations are too big for Australian supercomputing. Now, what I wanted to show here was the very difference. So this image is the, I have to go back. This image is the smooth blade. So the reference smooth compressor blade. And remember, this is that annulus of the compressor that I've unwrapped. And now these are these rows of blades that are sitting one above the other in the linear cascade. This blade is the smooth one. And now I apply the micro-riblets, which are so small that we can't even see them. And yet we see that the boundary layer has thickened here. And we see a significant difference in the flow. Even though the riblets are so small that I can't see them, they're doing something to the flow. We looked at, if we look back at this page, this is what's called at a nominal inflow angle of 60 degrees. This is the design angle where the plane would be flying, where the engine would be operating at cruise, for example. So most of the time that the plane is in the air, it's going to be at this design inflow angle. That's the inflow of the air coming in here at the left. It's coming in aligned with the blade at 60 degrees. However, when the plane is actually going through, for example, ascent or descent, so when it's speeding up to get up and trying to generate lift, the angle, the airflow coming into the engine is changing. And so these jet engines not only need to be efficient at that design point, they also need to be able to cope with misalignment of that incoming airflow, also for gusts, for example. This is also relevant for terrestrial gas turbines because when they're off, when we ramp them up very quickly, as I was talking before, to be used as peakers in the grid, this is also going to be a misalignment of the incoming airflow to that compressor blade. And so engine manufacturers or engine designers are also very interested in looking at what we call off-design inflow angles. So we can't just look at the design angle, but we need to look at either side of this, positive and negative, to see how that blade performs over that full envelope of expected incoming airflows. Here we have what's called, this is the stagnation pressure loss coefficient. Basically, it's a measure of efficiency. Lower is better. And so happily, we see this was a study done by that modeling that I was talking about, that desktop type numerical simulation of fluid flow by our collaborators at GE. And they did this sweep. So looking at different angles, different air angles coming into that compressor blade and what you get for the loss. Happily, as expected, the loss is the lowest at the design angle, and it starts to sharply increase once you move away from it. So if the airflow is coming in too high, or if this is my blade, if the airflow is coming up like this at positive incidence, or it's coming at negative incidence, it's misaligned with the blade, and therefore you get an increase in losses. And so we looked at this, what's called the loss bucket, and in collaboration with, this was where the input from GE was very important to tell us which angles are typical in their operation. And so they told us that 60, obviously we're going to do the design angle, but we're going to look at a positive inflow incidence of 63 degrees and negative at 54. And these are typical values that they're interested in. Already we start to see the mismatch between the RANs, so the desktop software, where a lot of the turbulence is modeled, and our case, our HipStar direct numerical simulation, where all of the turbulence has been solved for. We see a mismatch between the two approaches. And obviously we believe ours is correct, because what the RANs is doing is mispredicting the flow separation, for example, or mispredicting where the flow is transitioning from a laminar to a turbulent flow, which we'll see in a moment. So already there are issues, and this is just the smooth blade, and actually there are no adequate models for that riblet case, which we're going to look at. So when I look now at my riblets, so what this does over the blade, this is again that pressure coefficient over the surface of the blade. At nominal incidence, we're looking a loop over the blade. It looks like this. And what we're doing with just that tiny, a few degrees misalignment is creating very different pressure conditions over the blade. So we see that this is an important thing to do, that it's really changing what the flow is doing over the blade, just a few degrees off inflow angle. And this is actually what we're going to look at to judge what our riblets are doing. So this is a measure of drag. This is the skin friction coefficient, a measure of drag over the blade. On this side, so positive X is the top side of the blade, which I'll show in a moment. And on this side, we have a negative on the underside of the blade. And again, we have very different where it peaks. So if we just focus on the orange curve here, where it peaks like this, this is where the flow is laminar coming in, and now it's going to transition to turbulence. I'll show you what that looks like just in a moment. And we see the point of transition changes depending on if this is a negative inflow incidence happens much later. And at the positive inflow incidence case, it's basically turbulent along the whole blade. So we get a very different flow condition. And so this was why we really needed to get that input from GE to tell us, hey, it's not enough just to look at the nominal design point, but you need to look at points off it as well. Okay, so what riblet geometries did we choose? We went for this triangular shape, and we need to size these riblets. This is again one of those that Reynolds number that I was talking about before. We need to size it correctly. So that spacing is reliant on a viscous scale that depends on the flow speed over the blade. And so we need to size it correctly. And we sized it, that viscous scale, which is to do with this skin friction over the blade. This is really from fluid mechanics, so it's not so important, but we need to pick the right spacing depending on the speed of the blade, okay? And so we did that from the reference smooth blade case, and so we can come up with a riblet geometry. We went for smooth edges because this is more realistic from a manufacturing point of view, and also it's going to be very difficult to cut out the bottom. And we think that this is a more representative geometry than in fundamental fluid mechanics studies. They've been looking at these sharp riblets. So we went for a sharper riblet, which we expect will be more effective, and also the lower riblet. I want to say what this spacing is in physical units for the riblet. So if my physical compressor blade is around 10 centimeters long, this riblet spacing is about 50 microns. This spacing between these two peaks. So it's very tiny, and it's going to be very expensive to represent this on a computer. So this is what they look like. We can just simulate we looked at preliminary simulations. We don't have to simulate the whole compressor blade from the hub to the tip. We can just simulate the middle of it. So this is called a mid-span analysis, and we did preliminary work to figure out how narrow we can go, because we want to go narrow because it's expensive. So if you count really fast, you have 160 riblets across here. And if I cut through, again, we can't really see them. This is looking at the front of that blade. It's very tiny riblets. And if I look another another cut through, zoom in, sorry, I can see, and I mentioned, so we're on the order of tens of microns here, practically, and the flow is running over the top of those riblets. Some computational details here. So this is a forcing method. I won't go into that too much, but here we have what the grid looks like to represent, so that vorticity image that I showed you before, what it was. We have a background grid to represent all that background flow, the turbulent flow. And then we have this much finer grid around the blade because we need to resolve, you saw that intense turbulence at the surface of the blade. And so these two grids are interpolated between each other with a fourth order method to make sure it's accurate. Okay, this is what it looks like. This is how we represent the riblets on the grid with a type of forcing. So we force the velocity to be 0 at the surface of this surface. And so we can use a Cartesian-like grid here. This is in the span. So this is what my grid looks like. My riblets look like numerically. All of this adds up to many, many grid points. And these are required resolutions to make sure that we capture all of the turbulent energy. These are some requirements, again, from fundamental fluid mechanics studies. Basically, it adds up to around 4 billion grid points for the riblet cases. So this is solving those equations of fluid flow 4 billion times. For each time step. And we need to run this quite a long time to get average statistics. This adds up to 10 to the 15 degrees of freedom. So cannot do it on my laptop. And this is where the supercomputing comes in. So we've seen an enormous increase in supercomputing in the last few decades, which we've gone from 10 to the 15 petaflops. This is now 15 or so years ago, mainly powered by CPUs. And now we have hybrid CPU, GPU systems. So GPUs originally developed for gaming, and then someone figured out that they can do simple maths very fast as well. So really the latest big supercomputers now is Frontier. So Summit is where these simulations were done, was superseded by now Frontier. And they are backed, all that computational grunt is coming from these GPUs. And this is that Insight Leadership Computing grant that we had to allow us to use the computational facilities in the US. So what does this look like practically in the code? This is a snippet of our Fortran code. And what we do is this is a nested loop. It's nested 4 times. Basically looping over each nvar is each physical quantity in our equations that we need to solve for, and then the grid is 3-dimensional. So then we loop in 3 dimensions. So this is a very big nested loop. And what it says, what happens when the code, when we compile the code, is we tell it, we put in these directives, we say, do this bit in parallel on the GPU, and then it can string out it can figure out, depending on the compiler and the hardware, how best to accelerate this. And so it doesn't have to happen serially, but in parallel. Our code shows a 25x speed up for using these GPUs in this way. And GPUs are more energy hungry than CPUs, but even with that factor of the energy consumption, Hipstar is still our code 6 times more energy efficient on Frontier node. So using GPU computing. So we hope that, we want to improve the energy efficiency of the gas turbine, but also GPU computing is energy efficient computing. And so this has been very important for us to enable these types of simulations. So what did we get for all that computational grunt? We got these types of results. So this is what the velocity contours look like over the top of the blade. So for the smooth case, we have a smooth flow coming in. So it's a laminar flow. And then at some point here, it transitions to a turbulent flow. When I put the riblets on, they're so small, we can't see it here on the surface, but they're causing an earlier transition. And also for the shallower riblets, we're seeing a different flow again. But what we're really interested in is, are they reducing the drag? So this is the drag curve, if you like, for the smooth case. Here on the right-hand side, we have the orange curve here is for the smooth reference case, and we want to see the riblets hopefully reducing this curve. And they did, which is great. So they worked in the same way as on this is different to previous riblet studies. Previous riblet studies were always done on a flat plate, okay, with no pressure gradient happening over the surface. And so we weren't sure whether they would work in the same way here. We were hoping with these results from literature would translate, but we weren't sure. And so they caused this earlier, this peak in skin friction or peak in the drag is the signal for transition. We saw an earlier transition, but then the riblets were able to reduce the drag over the rest of the blade where it's turbulent. So riblets only work to reduce drag when it's turbulent. Okay, and the shallower riblets, which we thought might be a bit easier to manufacture. Remember, these things are 50 microns in spacing. Were also effective, didn't bring transition forward, but were also effective to reduce the drag. We see different results. This was at the negative inflow incidence. So remember that inflow angle now coming in back from being aligned. We see very different flow conditions over the top of the blade. So these are again, the contours of velocity. So again, reinforcing the importance of looking at these types of things at other inflow incidence angles. And here is the positive inflow incidence angle where the flow is turbulent over the full blade. And so the riblets can do their thing and reduce the drag over the entire blade. I'm going to skip ahead now because I've seen I'm running out of time, and just to one last bit. Here, where we're looking for, so we're happy that the riblets can reduce the drag over the surface, but we're looking now for other uses of the riblets. And here we have on the back end of the blade, I'm looking over the top, I'm looking at the pressure field. So we're interested also, a big concern in aviation is noise. And so whether the riblets could also do something to dampen the noise. Now the pressure field is a proxy for noise levels because that's where the noise comes from. And so if we look at the pressure over the back end of the smooth blade surface, we can see it looks like this. And then the idea we've seen from the literature is that not a riblet, but a serrated trailing edge. So something that looks like a triangular edge on the back end of a blade, which is something that's been tried in the literature, serves to break up larger scales, so larger structures in the flow, and to reduce them into smaller vortices here, smaller structures. And they found that they were able to reduce the noise level in their case. And so if we apply a riblet like this, we found lower pressure levels. And so we hope I need to do some more work on this, but I hope this will also translate into a lower sound level, noise coming from the blade. Okay, so I think I will leave it there, and I'd be happy to take any questions, but just to sum up, the gas turbines are playing an important role in the energy transition. I hope I convinced you of that. They're producing electricity, supporting renewable uptake, especially in Australia, but also there's the potential for cleaner fuels, for example, hydrogen, to be used in a gas turbine. Gas turbines are agnostic to this, although there's some technology development required for the combustor, and indispensable for aero propulsion for large long-haul aircraft, for example, that on which we're dependent on in New Zealand and in Australia. But future gains in efficiency and the development of more radical blade designs to try and keep pushing that efficiency up is hampered by the inaccuracy of those current desktop design tools. And so we argue that there's a space for high-fidelity simulations, so direct solution of the equations of fluid flow, but for this we need supercomputing, and we found this was a demonstration of world-first simulations resolving microscaled riblets over the high-pressure compressor blade at full engine conditions. So I will leave it there, and thank you for attending, and I'll be happy to take any questions.
Can you hear us? Melissa?
Yes.
Oh, good, good. Okay. So thank you very much, Melissa. That was you made a great effort to make it relevant and understandable for those non-experts in the room. So thank you very much for that. So any questions? Yeah.
I found that an absolute pleasure to listen to, Melissa. That was fantastic.
Thank you.
I represent a company that has developed a small-scale wind turbine. Has a 1.8 metre long blade, and we've aimed our Reynolds numbers at between 600,000 and 700,000. So we've got a pretty strong interest because the machine is stall controlled exactly where that separation happens and making it consistent. I think we've had some bad results from inconsistent stall initiation, and I'm very interested in this idea of ruffling the surface in some way to make that stall point consistent.
Yes. Yep. Yeah. So we saw that the riblets were able to. So the riblets reduce drag when it's a turbulent flow, but when it's a laminar flow, it could provoke transition.
Yes.
Yeah. But you saw it also dependent on the flatter riblet didn't do that, but the sharper riblet did. So, but it's could be used for transition control.
Have you done any work with wind turbines at all, or is it?
No, no, I haven't. No, but there are, I guess it's also an aerofoil, and people have put riblets. As I said, I know about the fuselage efforts, but on wind turbines, no.
Fantastic. Just one other little question too. I was wondering, in our case, fouling is a bit of an issue too. You know, we get bugs splattered along the leading edge and things like that. Is that an issue with gas turbines at all? I suppose it's more with turbining rather than the compressor engine.
Yeah, correct, exactly. The compressor I think stays pretty clean. We tried to. That was also why we used the rounded bottom for the riblet and not a sharp bottom, because we thought, you know, if there's some fouling, that's more representative of that. Turns out the trough of the riblet is not so important. It's more that spacing, because not much of the flow seems to get into that trough anyway. But fouling in the gas turbine is more a problem, yeah, and roughening of the surface on the high pressure turbine. So that's what my colleagues have studied. Basically, the turbine blade gets very rough from a range of reasons, and those ceramic coatings crack, for example, and that changes the transition point very much so, and really increases the heat transfer and therefore the danger zone for that turbine blade.
Oh, fantastic. Thank you very much.
Thank you.
So any questions online at all?
Yes, Cam Smart here, from retired engineer living in Wellington. A lot back in the mid 1950s, the main or the frontline fighter in the RAF was a thing called the Hawker Hurricane, which had air intakes at the leading edge of the wing roots. And my understanding is it had guns in front of those air intakes, and when the guns were fired, shock waves from the muzzles of the guns went into the air inlets, air intakes, got into the first stage of the compressor and stalled the blades. And this was a very serious thing, because essentially it meant if the compressor was stalled, the fire went out, and the airplane had to dive to a very low altitude before it could do anything again, even if the engine would start. So I'm just wondering if your riblets would control or exacerbate stalling effects.
Yeah, that's a great question, and definitely something G was interested in as well, whether they would help. So I guess we're talking about the flow separating off the back of the blades. So if I can find,
that's what I would assume too.
Maybe I can find some image of what that looks like. We might have to go all the way back to. I'm sure I have. basically in this case where it's at the positive inflow incidence, you can see it's not attached anymore. We don't see this with the flow is separated from the back of the blade. And so GE was also interested whether this could help keep, and we see that the drag coefficient essentially goes to 0 because the flow is separating.
Oh, yes, okay.
Yeah, so that's what's happening. The riblets, this was a question whether they could increase the operability of the engine, so to try and cope with stall. I didn't see it here. It didn't seem to promote attachment. It will do that if more upstream, so it'll make the flow turbulent and kind of stick to the blade, but at the back it was still and potentially causing even more separation. So it didn't seem useful for that. But intakes are a very interesting problem, and I have a student I co-supervise that's working on curved intakes and trying to also, this is also a very challenging fluid mechanics problem against flow separation, very difficult to represent with those desktop simulation tools, and only high fidelity numerical simulation can capture that correctly. So that's another sort of related area. But in terms of keeping the flow attached, the riblets didn't seem to do that here.
Okay, thank you.
Thank you.